Imagine sending a tiny, harmless looking file to a server, and within 3 minutes, you're running commands on that system. No passwords, no brute force, just remote code execution. That's the danger of insecure deserialization. This is episode 6 of the Vulnerability Chaining Masterclass. In episode 5, we chained local file inclusion, file uploads, and log poisoning into RCE. If you haven't watched it, make sure you do after this. It shows how small features can stack into catastrophic compromises. Quick legal note. Everything you'll see here is built in safe labs with intentionally vulnerable apps. Never test these techniques on systems you don't own or without written permission. Learn responsibly, disclose responsibly. And remember, this is about defense and education, not exploitation. Here's today's roadmap. Step 1. Malicious input. Attacker crafts a serialized payload. Step 2. Insecure deserialization. The app blindly processes it. Step 3. Gadget chains. Legitimate code paths linked for malicious ends. Step 4. Remote code execution. The attacker runs arbitrary commands. Stats tell the story. Only 8% detection. 3.2 minutes to exploit, and over 90% success rates. In short, if this vulnerability exists, attackers almost always win. Serialization is like packing Lego pieces into a zip bag so you can rebuild the model later. Deserialization is unzipping that bag and rebuilding. Now, what if an attacker sneaks in a dangerous Lego piece? The system rebuilds it without question, and suddenly you've assembled a bomb. That's deserialization risk. Reconstructing untrusted input into live objects without validation. This isn't limited to one language. In Java, it's object input stream.read object function and gadget chains like Apache Commons. In Python, it's pickle.loads function, which data scientists use daily. In PHP, untranslated function enables object injection and pop chains. In .NET, binary formatter.deserialize function has fueled RCE bugs. In Ruby, marshal.load function and ERB templates have been abused. Detection? Poor. 87% evade static analysis, 93% bypass WAFs, and most abuses rely on built-in language features. In other words, this is everywhere and almost invisible. Let's make this concrete with a real-world microexample and the canonical deserialization attack chain. Start with the chain. It always follows the same 4 steps. Malicious input, to insecure deserialization, to gadget chain, to remote code execution. In plain terms, an attacker supplies a crafted serialized object. The app deserializes it without validation, a sequence of innocent classes, that's a gadget chain, and is abused to perform actions. And finally, arbitrary commands run on the server. Now the sidecode example ties this together. An attacker delivered a view state payload, base64 encoded. The server deserialized it with no validation. Apache Commons invoker transformer was used as the gadget, and that led to command execution. The scale was severe. Around 78% of targets remained vulnerable for 30 plus days. Hundreds of successful breaches were documented, and average breach cost was multi-million dollars. So when you see deserialization in a code path, don't treat it as an isolated bug. Map it to the 4-step chain, look for gadget-prone libraries, and prioritize fixes urgently. These are the hot targets. 1. Sidecore view state. 2. Bento ML platform using Pickle. 3. SAP NetWeaver with RMI objects. 4. Fox CMS with unsafe unserialized function. 5. Python Pickle in supply chains. Across them, success rates range from 78% to 87%. Average patch times, 46 days. That's nearly 2 months of open exposure. In 2025, deserialization ranked as the 3rd most exploited web vulnerability. Average, 28 attacks per application per month. Growth, 21% year over year. Severity, 14% of all high severity RCEs trace back to deserialization. This is not rare, it's systemic. Every language has weak points. Java's commons collections gadgets, Python's pickle __ reduce __, PHP's magic methods and pop chains, .NET's binary formation, Ruby's marshal.load. Common failures, 92% lack input validation, 78% use dangerous classes, and 65% trust serialized data too much. In other words, developers open the front door and attackers just walk in. Why does this lead to RCE so often? 4 reasons. 1. Gadget chains. Innocent classes chained into weapons. 2. Lack of validation. Apps trust incoming objects. 3. Dangerous classes. Constructors or destructors that execute code. 4. No integrity checks. No cryptographic proof objects are safe. Every big breach we'll cover today maps back to these 4 mistakes. Think of gadget chains as Lego gears. Alone, they do nothing. Connected, they move powerfully. Attackers chain methods together to perform actions developers never intended. Examples. 1. Java. Invoker transformer in Apache Commons. 2. PHP. Pop chains via __ destruct function. 3. Python. __ reduce __ leading to os.system. 4. Ruby. Marshal with ERB templates. Detection? Less than 7%. Success rates above 90%. Gadget chains are stealthy and devastating. In Java, attackers serialize an object, send it via HTTP or RMI, and the app deserializes it blindly. Apache Commons collections chain fires, reaching runtime.exec function. Results: reverse shells, persistence, complete compromise. WAFs miss 89% of these payloads, scanners miss 76%. The fix: JEP 290 filters, serial killer library, and patching Commons collections. Fox CMS is a classic PHP example. The app unserialized user-controlled input. Attackers used magic methods like __ destruct function to trigger RCE. Metrics: 92% success, under 5 minutes to exploit, persistence on 76% of installs. Defenses: replace unserialized with JSON or use allow / classes. Lesson: if user input touches unresolved function, you're basically handing over the keys. Pickle is Python's silent killer, especially in ML. Attackers hide payloads inside trained models. The moment a data scientist loads it with pickle.loads function, the code executes. Let's go through this Python pickle attack. We are not running any code here. Instead, I'll describe the lab steps, the harmless outputs you'd expect to see, and the defender signals to watch for. Everything shown is safe and non-actionable. Step 1. Create malicious object. Attacker crafts a serialized Python object that contains a harmful behavior. Step 2. Serialized and encode. The object is serialized and typically base 64 encoded for delivery. Step 3. Deliver to pipeline. The serialized artifact is uploaded or submitted to an AI/ML pipeline or model serving endpoint. Step 4. Automatic RCE execution. The vulnerable service deserializes the artifact, no validation. 73% of ML pipelines are vulnerable, and most data scientists don't even know pickle is unsafe. Safer alternatives: JSON or message pack. But remember, convenience kills. Right now, attackers are focused on 1. Sitecore, 2. SAP NetWeaver, 3. Palo Alto Checkov, 4. Node.js, Node Serialize, 5. Spring Framework. All widely deployed, all actively exploited. Here are the action items. Patch now, segment networks, replace unsafe libraries, enforce allow lists. Here's what a real breach looks like. Sitecore. First, January 15, 2025, vulnerability discovered. Second, February 10, 2025, weaponized. Third, March 25, 2025, mass exploited, over 5,000 servers hit. Fourth, April 10, 2025, patch released. Impact: 17 terabytes stolen, $7.2 million per breach. Average detection time: 46 days. Failures: no validation, no MAC integrity, WAF bypass. A perfect storm. Here's the attacker's toolbox. Gadget chains mapped by language. 1. Java, invoker transformer and JNDI. 2. PHP, destructors and magic methods. 3. Python, __ reduce _ and subprocess calls. 4. .NET, object data provider. 5. Ruby, ERB template evaluation. Detection: just 7%. Every one of these bypasses WAFs. Why do these chains work so well? Because 1. WAFs can't parse object graphs. 2. EDRs don't see code execution inside legit processes. 3. Gadget chains are too complex for signatures. That's why exploitation succeeds over 90% of the time. Defense requires layered strategy, not single tools. How do we break the chain? First, allow list classes, deserialize only what's safe. Second, block gadget chains, strip dangerous classes. Third, integrity controls, cryptographically sign serialized data. Combined, these cut risk by 97%. That's the difference between compromise and containment. Here's what it looks like in practice. Number 1, CI/CD gates reject unsafe code before shipping. Number 2, RASP monitors runtime deserialization. Number 3, automated incident response isolates compromised containers. Financial institutions using this playbook saw 89% attack reduction and 0 breaches. Proof that defenses work if you implement them. Here's security toolkit. 1. For red teamers, YSO serial, PHP GGC, .NET serial, and exploit generator. 2. For defenders, pickle scan, contrast assess, dependency check, and cloud alerts. What's more important here is that the offensive tools are for labs only. In production, stick to monitoring and scanning tools. Don't blur the lines. Here's the cheat sheet. 1. 28 attacks per app per month. 2. Less than 14% detection. 3. Nearly 90% success. Top CVEs: Sitecore, BentoML, SAP NetWeaver. Immediate actions: patch, replace unsafe functions, enforce allow lists. That's the wrap up. If you missed episode 5 on LFI plus file upload plus log poisoning, watch it after this. It sets up how small flaws escalate into RCE. And next up, episode 7, DOM XSS plus CSP bypass escalate to session hijacking, browser-side attacks that steal entire accounts. Subscribe and set your reminder. You don't want to miss it. This is Bug Bounty and Beyond, where we don't just break things, we build the future of security. Thanks for watching. Stay secure.